Hello, my name is Nguyen Khoa, and I'm an 11th grader from Nguyen School in Hanoi, Vietnam. Today, I'll be presenting my findings on a research about 4-coil wireless power transfer systems for underground mining applications. The study aims to provide a safer and more efficient alternative to wired electrical systems in underground mining environments. Underground mining is one of the most hazardous industries, facing numerous challenges and conditions, including confined spaces, explosion risk, and high humidities. Among these, electrical leakage from traditional wired systems is a major cause of accidents involved with underground mining. Therefore, the introduction of the wireless power transfer system proposed by Nikola Tesla in 1891 can provide a breakthrough solution for powering mining equipment, monitoring sensors, and lighting systems while reducing risks associated with electrical leakage. The research was done based on a theoretical model simulated based on Kirchhoff's law and the equation shown here. The wireless power transfer system consists of 4 coils. Coil 1 is a transmitting antenna coil that is connected to the power source, and coil 4 is a receiving antenna coil which is connected to the load. Coils 2 and 3 are the resonant coils placed between the 2 antenna coils to improve power transfer and were optimized by calculating the coupling coefficient. The transmittance coefficient S21, which will be used later in the research, can be determined using the following formula. The efficiency of a wireless power transfer system largely depends on the coupling coefficient. This coefficient is influenced by 2 main factors: the distance between the coils and the dielectric properties of the surrounding environment. By using simulation and theoretical calculations, we can analyze how changes in the transmission distance and the rotation angle between the coils can affect the overall efficiency of the system. We simulated the wireless power transfer system using the high-frequency structure simulator. The simulation experiments focus on evaluating the influence of the energy transfer distance, D2, and the rotation angle between the coils, alpha, on the transmission efficiency. All the coils are made of copper with a winding diameter of 5 mm. The antenna coils CD1 and CD4 have identical dimensions, and in operation, CD1 is connected to a radio frequency power source set at 13.5 MHz, while CD4 is connected to the load. The 2 resonant coils, CD2 and CD3, are identical in physical parameters. Each coil is designed with 6 turns on the same plane, and the space between the turns is 3 mm. This table shows the technical specifications and parameters of the system. Based on our design, the inductance of each resonant coil was calculated using Q3D software to be approximately 12.837 microhenries. To achieve a resonant frequency of 13.5 MHz, we connected a 10.8 picofarad capacitor across the 2 ends of each coil. For the simulation, we set the frequency range from 10 to 17 MHz, with small steps of 0.02 MHz to ensure accuracy. To study how transmission distance affects energy transfer efficiency, we varied the distance between the coils from 5 to 30 centimeters. For the rotation angle analysis, we fixed the distance at 22 centimeters and adjusted the angle from 0 to 90 degrees. Moving on to the results and discussion, we'll first talk about the effect of distance. In figure A here, between 22 and 30 centimeters, the S21 characteristic curve has only 1 resonance peak at 13.5 MHz, whereas from 5 to 22 centimeters, the S21 characteristic curve has 2 resonance peaks, and the distance between the 2 resonant peaks increases as D2 decreases. This can be explained by the decrease in D2, which leads to an increase in mutual inductance between the 2 coils and resulting in the frequency of the 2 coils being separated into 2 frequencies. And because the coupling coefficient between the resonant coils CD2 and CD3 decreases as D2 increases, the transmission coefficient S21 also decreases. According to the simulation results and theoretical calculations, when D2 increases from 22 to 30 centimeters, S21 decreases from approximately 0.98 to 0.77 at the frequency of 13.5 MHz. Similarly, the energy transfer efficiency decreases as the distance D2 increases. At a distance of 22 centimeters, the efficiency reaches 98%, while at 30 centimeters, the efficiency drops to about 60%. This figure represents the magnetic field density distribution of the 4-coil wireless power transfer system corresponding to the distances 25 and 30 centimeters at an angle of 0 degrees. From figures A and B, it can be seen that the magnetic field density distributed on coil CD3 and CD4 at 25 centimeters is larger than at 30 centimeters. Likewise, the electric field density distributed on coils CD3 and CD4 at 25 centimeters is also larger than at 30 centimeters, as observed in figures C and D. Now, I'll discuss the effect of the rotation angle between coils. Figures A and C show that the coefficient S21 decreases when the rotation angle alpha increases. This is explained by the fact that when alpha increases, the coupling coefficient K23 between CD2 and CD3 resonant coils decreases. To be more precise, when alpha is 0, 30, 60, 70, and 90 degrees, S21 is 0.99, 0.98, 0.94, 0.77, and 0.33 at the frequency of 13.5 MHz respectively. This trend also applies to the energy transfer efficiency. As can be seen from figure B, the efficiency starts to decrease sharply when the rotation angle alpha increases to around 70 degrees. And when alpha is equal to 90 degrees, the energy transfer efficiency is roughly 11%. Then, the magnetic flux from coil CD2 almost does not sweep through coil CD3. Figure A compares the transmission coefficient S21 across simulation, theoretical calculation, and actual measurements at a rotation angle of 0 degrees and a coil distance of 22 centimeters. The results show a strong agreement as S21 was 0.98 in the simulation and 0.96 in the measurement. Similarly, comparisons at a rotation angle of 70 degrees are shown in figures C and D. At 13.5 MHz, the S21 value was 0.77 in both the simulation and theoretical models, while the measured result was around 0.7. In terms of energy transfer efficiency, the simulation showed 60% and the measured efficiency was 49%. Overall, the experimental results align closely with the theoretical and simulated data, confirming the accuracy and reliability of our model, and notably, the efficiency we achieve is higher than in previous studies, largely due to optimized impedance matching between the coils. This study has designed and evaluated a 4-coil wireless power transfer system tailored for use in underground mining environments. Within the tested range, the system achieved an impressive efficiency of 92% at a transmission distance of 22 centimeters. While these are still early stage results, the strong agreement between our simulations, theoretical calculations, and real-world measurements gives us confidence in the reliability of our model. Looking ahead, we plan to expand this research by testing the system under real mining conditions, including variations in temperature, pressure, and gas composition, to further optimize its performance and practical applicability. Thank you for listening.